Section 3 on hyperbolas. This will be the second video that we're going to do for this particular section. The previous video for this section will just go over we'll have gone over the derivation of the standard form of the equation of a hyperbola that's oriented horizontally. So we started off with the definition in that video given here. A hyperbola is a set of all points in a plane such that the absolute value of the difference of the distances from two fixed points is constant. So the idea is that if you take a point and the distances from that one point to the two foci, and we subtract them instead of add them. If you add them, you get an ellipse, and if you subtract them, you get a hyperbola as long as it's a constant absolute value of the difference. Because differences can go one of two ways. It can be negative or positive. It could be zero also if the two distances are the same, but we're setting it equal to a particular constant, non-zero, and we want it to have the same sign all the way throughout. Doesn't matter what the sign is. Or we want it to have the same value all the way throughout. We don't care what the sign is. So we end up getting this type of a figure. We have some point along the curve. There are two foci, and we're taking the difference or the distance between those two foci and that one point. We're subtracting that difference, and it's going to have a constant difference. And that's going to form this hyperbolic curve. It looks like two parabolas, but they're not necessarily parabolas. So it's not the exact same shape. Slightly different. The hyperbola looks parabolic locally, close to the center, but globally, if you really zoom out far enough, then these two curves turn into straight lines, pretty much. So they will approach two straight lines. Those two straight lines are what we know as asymptotes. It has asymptotic behavior, and there are two straight lines centered, or that pass through the center of that hyperbola. So these two fixed points didn't have it. These are foci, and I'm writing in red. I should be writing in black. So those are the two foci. We have a focus and another focus. Both of those foci are inside of their respective curves. The left foci is inside the left curve. The right foci is inside the right curve. And by inside, it's a similar term to what I used for parabolas. So we will look at example number 1. So for example number 1, graph x squared over 4 minus y squared over 25 is equal to 1. Sketch the asymptotes, find the coordinates of the vertices and the foci. So much like an ellipse, we have two axes, if you want to think of them, two axes of symmetry, that is. But those axes don't play the same way that they do with ellipses. Because in ellipses, there are intersection points which define vertices, co-vertices, and that's also going to have a particular length involved. These axes, they have an infinite length, and that's because the ellipses go on forever on one side. They have a boundary, left or right, depending on which lobe we're talking about. But these two numbers, 4 and 25, are not going to give us the sizes of the axes. It's going to give us the size of a box that we're going to draw at the beginning. So if x squared over 4 minus y squared over 25 have no translations, no apparent translations, this figure is going to be centered at 0, 0, the origin. So we have a center, and we're going to draw a box according to these dimensions. That's a 2 and a 5, because 2 squared is 4, 5 squared is 25. So what I'm going to do is I'm going to draw a box that's going to be a half width of 2 and a half length of 5. So that means from -2 to +2, and then from -5 to +5. So I got that A was 2 and B was 5 from 4 and 25. So the one that's underneath X is going to tell us the horizontal width of this box. The one that's underneath Y is going to give us the vertical width of the box. So the horizontal width is 2, left and right, so plus minus 2, so left and right. And then the vertical width of the box is going to be up 5 and down 5. So then I'm drawing a box, and I'm going to do this with dotted lines, or dashed lines, because these are technically dashes, not dots. So what is that box for? The box is to tell us what the asymptotes look like. So what I probably should do is, if I have a horizontal hyperbola, this is x squared over a squared minus y squared over b squared is equal to 1. So we're drawing a box centered at the origin, so 0, 0. And from here to here, this is A. Also from here to here, this is A. From here to, let's say, up here, that's B. And then from here to the center again, it's B. Okay, so this is not going to play the same as with ellipses. A and B, it doesn't matter which one's bigger. A is always the one underneath X, B is always the one underneath Y. So the number underneath X, and we're not going to care about A's and B's. For ellipses, we don't care about A's and B's again. It's just whichever one's bigger, that's the one we're going to subtract from. So you don't really want to worry about which one's A, which one's B. What you want to worry about is what those numbers mean for the graph. So the number underneath X tells us the half width of the box horizontally. The number underneath Y will tell us the half width of the box vertically speaking. So then, the vertices, it depends on if this is oriented vertically or horizontally. The number that's positive, so if the X term is positive, this is horizontal. So horizontal if X is positive. Let me write that on the side, horizontal when X is positive. The X term, that is. It's vertical otherwise. Or not otherwise, it's vertical when the Y squared term is negative. So there are other situations where it could be slanted. Okay, so in this case it's horizontal. So then your vertices are along the horizontal axis. Let me draw a horizontal axis. So your vertices are in the horizontal axis in the same line as the same horizontal line that the center's on. So this is vertex 1, vertex 2. This is negative A, comma 0. This one is positive A, 0. Now that box is also going to tell us what the asymptotes look like. So what you do is you connect the diagonals of the box and then extend those to make straight lines that go outward forever on both sides. And then forever on this side too, as well. So what you do is you extend the diagonals of that box, and those lines that are the result of extending the diagonals of the box are the asymptotes of this figure. So once I have my vertices, which I've already drawn, then the rest of the figure just looks like this. It's a curve that will approach those lines as asymptotes. So you curve it out a little bit inside, and then you straighten them out outwards that way. And that's what that that hyperbola is going to look like. And that's basically it. So it's a playing around with the numbers A, B, and C. So sometimes they'll give you the equation, figure out what the graph is. Sometimes they just give you a little bit of information and figure out what the equation is. So much like what we did in the previous section. So what do I have left? I've already drawn the box. I've already figured out how big A and B are. So what I'm also going to do is I'm going to extend those lines this way. And I probably want to find, they're going to have me sketch the asymptotes, and if I'm sketching something, I need to label them. So the asymptotes have an equation. This is a linear equation, y is equal to mx plus b. In this case, it's just mx. b is 0 because we're crossing through the origin. And algebra 1's coming back again. So let's see, that's 5 over 2 for the slope, x. So 5 over 2. And where did I get that from? Rise over run. It moves up 5 and then to the right 2. The box tells you what the slope is. 5 divided by 2. Y divided by x. The other one is negative 5 over 2 because it's going to be the opposite direction. So this one's y equals negative 5 over 2x. There's a negative sign there. Handwriting's a little ugly, as it usually is. But there it is. So what next? So I sketched the asymptotes. That's good. Find the coordinates of the vertices. Your vertices are one of these 4 different points that I drew to make the box. Which one is it? Well, which one's positive? X squared's positive. Since x squared's positive, it's the 2 that are along the x-axis. Horizontal, not vertical. So I want those 2. So I've already sketched them. I'm going to have to label them. So the labeling of those 2 points, And they're also going to want the foci, so I probably want to do this a bit more carefully. That's going to be -2, 0. That's not very careful. 2, 0. That's very messy. Those are my two vertices. Then we're going to draw the rest of this curve, and it's going to go something like this. And like this. So those are my two vertices. So I might want to label them asymptotes, or not label them. I might want to summarize here. Asymptotes, y is equal to plus minus 5 over 2x. Vertices, plus minus 2 comma 0. So coordinates of the vertices and the foci. I still need the foci. Then they want the domain and the range. I kind of don't care about the domain and the range, but the foci. So there's an equation for hyperbolas, which I don't think they gave it up here, did they? No, they didn't. This is very, very poorly put together, this one section. But the equation for the foci, c squared is equal to a squared plus b squared. So very much like the Pythagorean theorem in this situation. So it's the addition of these two. So a squared plus b squared in this case. So then c is equal to the square root of, well, what are a and b? We found 2 and 5. So that's 4 plus 25, 29. Square root of 29. So the foci then, foci are also along the horizontal axis in this case if it's horizontal. So there are two axes, and I forget what they're called. And I'll have to look them up in a little bit. All right, so I looked it up. I should have had that looked up already. This major axis, which is no longer called a major axis. Major and minor are for ellipses. All right, so parabolas are simple. Parabolas are super, super easy. Probably like them a lot compared to these other two. So for a parabola, we just have one axis of symmetry. For an ellipse, we have a major and a minor. The major is the larger. For a hyperbola, it doesn't make any sense to call them major and minor because there's no one that's bigger than the other since they're both infinitely large. So the one that is analogous to the major axis, so the one that runs along the same as the orientation of the ellipse, the hyperbola itself. So if the hyperbola is horizontal, then the horizontal axis is called the transverse axis. Transverse axis, and the equation on that one is, in this case, it's going to be y is equal to 0. The other axis, which is just one perpendicular, so the one where there are no other vertices, there are just two vertices in this situation. But if we were drawing an ellipse, we wanted to call those co-vertices, and that were the minor axis. That other axis, which is perpendicular to the actual orientation or transverse axis, we call this the conjugate axis. That's the conjugate axis. Anything else that we need? Just the focal distance, so that would be c this way. So c comma 0 and then negative c 0. And the equation that links a, b, and c, I don't know if I gave it here somewhere, and I didn't. That's c squared is equal to a squared plus b squared, plus for hyperbolas, minus for ellipse. And it's the bigger one first. That should be pretty simple. So then the foci are along the transversal axis. In this case, that's the x-axis. And it's going to be square root of 29 added and subtracted from 0. So the foci are plus minus square root 29 comma 0. And that's everything they wanted besides the domain and the range. Domain and range. So if I look at the domain is everywhere that the curve exists, which wouldn't be negative infinity to infinity. It starts off at negative infinity, yeah. It goes off to negative infinity on the left, but it is limited to -2 on one of those sides. Now, I think there's brackets at -2 because there is a point with a x-coordinate of -2. Parentheses always for infinity and negative infinity. Union for the second half, the right half, +2 to positive infinity. And that's the domain. So I'll call that D for domain because I'm lazy and I don't want to write out the rest of the word. So what about the range? The range is every real number from negative infinity to infinity. So those are my domain and range sets. And that's everything they wanted in this particular example. Example number 1. So it's a matter of figuring out the box where it's centered. So there's several steps involved, and these can be a little tougher. So you find out where the center is at. In this case, since there are no apparent translations, x squared and y squared by themselves, there's no plus or minuses inside, then it's 0, 0 for the center. Then you look at the numbers underneath, and that tells you how big the box is going to be. 2 and 5, left and right, up and down, from that center 0, 0. So that's how I was able to draw that box really fast. That's your second step. So center first, then you draw the box second. So then after you draw the box, you want to go with the asymptotes by connecting the diagonals of the box and extending them as much as you can, and figuring out the equation of the lines that pass through those two, or that are characterized by those diagonals. And that's easier said than done. So this one was easy because it passed through the origin, and that makes it a little easier. If it doesn't pass through the origin, then you probably have to use point slope formula to figure out what the equation of that line is, which when you practice with that, it's easy too. That probably gave you nightmares back in Algebra 1, but it's pretty easy stuff if you see it again now. After you have those asymptotes, you draw the curve using the vertices that are along the transversal axis, and you'll know which one the transversal axis is, or the transverse axis, based off of which of these terms is positive. The one that's positive refers to your transverse axis. Then you draw the rest of the curve, and then you figure out whatever else they want you to figure out. In this case, they wanted the foci, which I got the foci, and then the domain and the range. That's just by looking at it. It's an Algebra 1 problem. So here are the standard form equations in both of those situations. Transverse axis is along the x, in other words, that's horizontal. And then transverse axis is along the y, which in that case, that would be vertical. And those are pretty simple. I'm not going to go by the numbers strictly, or by these formulas strictly. It's going to be based off of the box, and then what I see is positive, negative, and all that good stuff. So we're going to look at that in example 2. Example 2, we'll graph another one. And this one, if you look at the equation, you don't see any translations. And that's going to mean that we're going to have a center at the origin again. So we'll do another one of these. I'm tempted to stop there, but I think I'm going to go into example 3. And after example 3, that's it for this video. So it says give the equations of the asymptotes and the foci, domain, and the range. So domain and range again, of course. They're doing that for all these problems. So you want to look at the equation that's given, mess with it a little bit. It's not in standard form, so 16y squared minus 25x squared is equal to 400. So this is not in standard form, and the difference between this and something that is in standard form, the right-hand side should equal to 1, just like for an ellipse. So in this case, you see that we're going to have to divide by 400 on both sides, and if I divide by 400, 16 times 25 is actually 400, so you're going to get y squared over 25 minus x squared over 16 is equal to 1. And you could verify. 16 divided by 400 is 1/25. 25 divided by 400 is 1/16. Okay, so you'll notice the y squared is the leading term, which is positive. The x squared is negative. So what that means is the transverse axis is going to run vertically instead of horizontally. So what we do is we draw our box. So this is centered at the origin for sure. And how far left and right am I moving from that box? How far up and down? So then we don't worry about the A and B and where that's at and what the formulas for the vertices are and all that junk. So your center is at 0, 0. That's what you look for. So center first. Center's at 0, 0. And then you move left and right the amount of the square root underneath the x term. So this thing tells me that the left and right value is 4. This thing tells me that the up-down value is 5 because the number underneath y is up-down, the number underneath x is left-right. So 4 and 5. So left and right, 4. So there's a endpoint for the box there and there. And then up and down 5 from 0, 0. So top endpoint, bottom endpoint, -5, +5. And then we draw our box. You don't have to draw the box, but it's a good idea if you do it, because it's going to tell you where the asymptotes are at and what they look like. And you remember the asymptotes are the next step after drawing the box. So what we do is we look at that diagonal, and that diagonal connected here and here. So what's the slope of the line that forms that diagonal? Well, we'll take 0, 0, and then this point, which is 4, 5. So from 0, 0 to 4, 5, it moved up 5 and to the right 4. So a rise of 5 and a run of 4, that is y equals 5 over 4 x plus b, whatever b is. In this case, b is 0 because the y-intercept b is the origin, 0. Or the y-coordinate of the y-intercept is 0. So then this line has a slope of 5 over 4. So the next one would be 1, 2, 3, 4, 5, 1, 2, 3, 4. And I'm trying to connect the dots properly. 1, 2, 3, 4, 5, 1, 2, 3, 4 should look something like this. And that's my one of my asymptotes. The other asymptote goes down 5 to the right 4. So it's a rise over run of negative 5 and 4. So 1, 2, 3, 4, 5, 1, 2, 3, 4. No, that's 3, my bad. So 4 is here. So 1, 2, 3, 4, and that's going to be something like this. So then up 5, and then 1, 2, 3, 4 here. And that's the other asymptote. And the equation of that asymptote's y is equal to negative 5 over 4. It's the same slope except negative. And those are my two asymptotes. So they wanted the equations of the asymptotes. That's done. As long as that's done in the graph, that's going to be good enough. They want the foci. So how do I find the foci? Well, let's see. I'm going to call that A and this one B. Normally A is the one that's underneath X, B is the one that's underneath Y. So then A squared plus B squared is equal to C squared. So C is equal to the square root of the squares of those numbers, which are 25 and 16. I don't care the order, because we're adding. So then 25 plus 16, is that 41? None of these have been nice numbers. I don't like it. So square root of 41. So then where are the foci? The foci, in this case, the transverse axis, or analogous to the major axis, is vertical. So that means they're up and down. So square root 40, what's square root of 41? That's somewhere above 6. So somewhere here, because the square root of 36 is 6, and the square root of 49 is 7. So it's somewhere between 6 and 7. So those are my two foci. So that's F1 and F2 over here. So what does my curve look like? I'm going to draw that in a different color. Let's say red. The actual curve itself looks something like this. And it's not going to, I drew these dots here, but those dots were only to form the lines, to draw them a little bit better. They're not going to touch the asymptotes. So the curve looks something like this. And it looks a little slanted, but that's because of the way that I drew it. So where are those foci? The foci, I labeled them as F1 and F2. The foci are, what is it, 0? So the y-coordinates, or the x-coordinates, sorry, is 0. The y-coordinates vary, plus or minus the square root of 41. So it's up or down from there. So those are the foci. The asymptotes, I'll probably include it here in the summary. Asymptotes, y equals plus or minus 5 over 4x. And they're also going to want the domain and the range. They didn't ask for the vertices. That's weird. So they asked me to graph it, and the graph is complete. They didn't ask for the vertices, which I could label the vertices. The vertices were at 0, comma, plus minus 5. And then they also want the domain and the range. The domain is all real numbers. Domain, all real numbers, which I'm going to be even lazier and just write R. Range is the one that's a little tough. That one goes from negative infinity, stops at negative, what is it? Oh, and I drew this one wrong, didn't I? Very sorry if you caught that ahead of time. I make those mistakes a lot. That's a lot harder for me to do this without like students in the classroom, because you guys catch my mistakes a lot more often. I have nobody right now at the moment that I'm recording these to monitor and, hey, you're doing that wrong. So I have to rely on my own like wits, which are like terrible right now that we've been in quarantine. It's like my brain's turning into mush a little bit more. All right, so anyway, so we have negative infinity all the way to negative 5. That's square bracket. This is open parentheses, union, positive 5, and then positive infinity. And that's it for the domain and range. That's it for this particular problem. So that's basically all that you need to know. These are simpler versions of what they can actually show you. So how can they make this a little tougher? Numbers 1 and 2 had the center. I was going to call it a vertex, not a vertex. It's the center at the origin 0, 0. So the only way that this can get much tougher that I'm going to care about would be if you have a center somewhere else other than the origin, and that's it. So what's going to be harder about this? The only thing that's going to be harder about this would be finding the equations of the asymptotes. Then I have to resort to using or keeping track of the y-coordinate of the y-intercept. It gets a little tougher that way. That's not too bad. So we'll move on to, well, let's see, before example 3, summarization of those situations with off-origin centers. So if we have a horizontally oriented hyperbola, and in this case it's horizontal because the negative is on the y term, not on the x squared term. So if the x squared term is positive, not the y squared term. So if that's the case, the transverse axis is horizontal, and that's going to be y equals, for a horizontal line, k, because k is the offset value vertically. Your vertices run along this transverse axis, so the y-coordinate will be k for both. The x-coordinate, though, is going to vary. So the x-coordinate should be h, which is the center. That's the x-coordinate of the center, but it's going to be offset by the value of a. So it's h plus minus a, comma k. And here's the reason why. So there's a graph here, but that's way too cluttered. I'm going to draw a bigger one. So if I have a hyperbola, let's say it looks something like this. That's an ugly hyperbola, but I'll use it. So the center is along the transverse axis, that's h, k. Then the vertex, which that should be the vertex, is same y-coordinate, but the x-coordinate is moved to the right by a. So that's h plus a, comma k. The other vertex is the same distance a, but to the left. So that's h minus a, comma k. Same y-coordinate, though. So that's why it's h plus minus a, comma k. Foci. The foci have the same form, just a different number adding and subtracting. Instead of a, it's c. So then that's going to be, so this was here, and this one is h plus c, comma k. This one is, and this one is this one, h minus c, comma k. And that's the next thing, I think. H plus minus c, comma k. Then the equation for the asymptotes, that's going to be a tougher one. So you draw the box, and whatever b looks like, let's say b is that big. So we don't really know unless we have the equation. And we have this line is one of the asymptotes. So this line is y equals to mx plus b. Now, we're not going to use slope-intercept form. I'm going to use point-slope form. Y minus, and we're going to use the center as my reference point. Y minus k equals m times x minus h. That's actually the conics form of the equation of a line. So that's the conics equation of a line. So the point-slope form actually comes from conics. And if you remember, a line is a conic section. So h and k would be the center, but lines don't have a center, so that's why we never called it a conics form like that or a vertex form or anything else like that. The only thing here that we need to figure out is what's the value of m. Well, the value of m is the rise over the run. What's the rise? The rise is b, and the run is a. So m is b over a. For the one that's positive, what's the one that's negative? The exact same equation because it runs through the same point, hk. So y is equal to negative, I got to write y minus k equals negative b over a, x minus h. And that's this line. Goes through the center and goes this way. That's an ugly line. But that doesn't matter. So those are the equations for the asymptotes. Y is equal, or y minus k is equal, plus or minus b divided by a, x minus h. And that's actually going to be the same for the asymptotes of the other situation where that runs vertically. The transverse axis is vertical. So that's y minus k equals plus minus b over a, x minus h. And that's going to contradict the way that they wrote those here. So they have a and b. So I'm taking a to be the horizontal and b to be the vertical. It doesn't really matter. It doesn't matter at all. And then, of course, there's this equation that you have to be really careful to remember. C squared is equal to a squared plus b squared. Because those are getting added, we don't care which one's a, which one's b. It doesn't matter at all. So I take A to be the horizontal, B to be the vertical. So I'm going to call that B, and this one A. The only major difference is which one's positive, which one's negative. That's the one you want to care about. So then what's my transverse axis? It's no longer y equals, now it's x equals h. My vertices run vertical now, so that's going to be h, comma, k plus or minus b, if that were b here, and this were a here. The foci, h, k plus or minus c. And I think that's going to contradict what I did earlier, because I did actually leave it as A and B the way that they wanted, but I don't really care at this point. So it's really just how the figure is built. It's two box dimensions. One's vertical, one's horizontal. You just got to know which one you're using for which. It's not a big deal. So number 3, and after number 3, we're going to go ahead and stop here. So does this one run horizontally or vertically? And it should be pretty obvious. This one runs horizontally because the x squared term is positive. So because the x squared term is positive, this is going to run horizontally. So where's the center, though? So the center is at hk. And what you do, if you remember for ellipses and parabolas, you negate these numbers. If it's plus, it's minus. If it's minus, it's plus. So it's going to be 2, negative 4. So you switch the order, just like we did for circles way back in the first 6 weeks, or second 6 weeks. So it's 2, negative 4. So 2, negative 4 is my center. And that's the center of the box that I'm about to draw. So your very first step, so step number 1, center. And then you graph it. And that's going to be 2, negative 4. Step number 2, the box. You're going to do left and right how much? The square root of the number underneath x. So left and right 4, so plus minus 4. And then up and down how much? There's no number here. You assume it's a 1 if there's nothing there, so it's plus minus 1. So if there's nothing there, it's a 1. Unless, of course, this number wasn't a 1, then we had to divide first. But that was a 1, so I didn't even bother. So it's left and right 4, up and down 1. So left and right 4, 1, 2, 3, 4. That's left 4, 1, 2, 3, 4. That's right 4. Up and down 1. That's a very thin box. So that means these lines are not very steep. They have a very small slope. And the slope on those lines would be 1/4. Because it's a rise of 1, a run of 4. So that's going to be asymptotes first off 3. So asymptotes y, and it's going to be plus 4. So shortcut, you just take these, and that's going to be the pieces of your equation for the line. Y plus 4 is equal to the slope times x minus 2. And what's my slope? Plus minus 1/4. And that's x minus 2. So center, asymptotes, so I have the asymptotes down. Then they want the domain and the range. They don't even want the vertices. They're asking for less and less each problem. Okay, so then I'm going to draw those asymptotes. 1, 1, 2, 3, 4. 1, 1, 2, 3, 4. 1, 1, 2, 3, 4. I'm drawing as many points as I want to be able to draw an accurate line, which my lines are not really good anyway. And then 1, 1, 2, 3, 4. And then here. So to the best of my ability, I'm drawing these straight lines, which are pretty terrible, by the way. And then which way does my hyperbola run? That goes this way, because it's horizontal. X squared term's positive. So it looks something like that. It's very thin. So number 4, step number 4, if you wanted, we graphed. So we finished the graph of the hyperbola, and we did. And I think that's all they want. They could have asked for the vertices, they could have asked for the foci, but they did not, which I'm going to go ahead and give those anyway. They didn't ask for them, vertices, but you need this for your homework. So vertices, or for the test. Vertices are left and right from the center, which has a y-coordinate of -4. So for sure, y-coordinate's -4. Hopefully that's obvious. The x-coordinate's not super obvious, but I could take a look at the graph and I see that one of them's at -2, the other one's at +6. So I see you could build it this way where it's 2 plus or minus 4, but we have actual numbers. So that's -2, -4, and 6, -4. So I'm going to want the 2 points like that since we have the actual numbers themselves. And those are pretty easy numbers to add and subtract. So those are the vertices. What about the foci? Foci might not be so easy. And there's an equation for the foci. C squared is equal to a squared plus b squared. So that is 16 plus 1, or 17. So c is equal to the square root of 17. Where'd I get 16 and 1? I got them from here. There's a 1 down here. That's where I got those from. So then the foci. That one is going to be along the horizontal axis as well. Center is 2, so it's 2 plus or minus this number, square root of 17, -4. So because that's square root of 17, I can't really combine it with that 2. It stays that way. So those are the vertices and the foci. What else do they want? Domain and range. Domain, -infinity to -2, square brackets. Union, 6 to infinity. Hopefully that's obvious. Range, all real numbers. I'm going to box everything that they wanted. They wanted the graph. The graph's there. I'm not going to box the graph. The asymptotes, so I'm going to box the asymptotes. And then they wanted the domain and range, so I boxed those two. So I didn't box the stuff that they didn't want. But that's basically it for this particular section, and that's going to be it for the chapter 10. And also, because this is the last week for the 6 weeks officially that we're going to be taking grades, that's it for the year. So for those of you that are watching this video, congratulations. That's the end of pre-calculus for this particular year. So we'll go ahead and stop here.